Friday afternoon before reading week. It's great. You spent some of your free time with us, and it is for a very good reason, and I'm sure you will not regret coming here. It's our great pleasure to welcome Audrey Sedal from McGill. Audrey has joined McGill from, if I remember correctly, Toyota Technological Institute was your last position, after doing a PhD in University of Michigan and graduating from MIT with a bachelor's. And Audrey was also named one of the rising stars in mechanical engineering in 2019, right? So I think we're in for a treat today. I very much look forward to your talk on morphology and structure in robotic intelligence. Thanks so much for being with us. The stage is yours.
Thank you. Is it working? Okay. I think I want to calibrate a little bit. Raise your hand if you're from a computer science background. Okay, great. So my postdoc was in computer science. I've learned to speak CS a little bit. Raise your hand if you're from an engineering background. Okay, mechanical or aerospace? All right, electrical or aerospace? Other?
Chemical.
Chemical?
No.
Okay, yeah, well, other, can I ask what that might be?
Machine learning.
Machine learning. Machine learning engineering? Okay, cool. Yeah, we don't have a program like that at McGill, so I'm glad to learn about it. So yeah, so the title of my talk today is about the role of morphology and structure in robotic intelligence. I am an assistant professor at McGill in mechanical engineering. I'm also an associate academic member of MILA, Quebec AI Institute. And my research group is called the Robotics, or the Mechanics, Actuation, and Computation for Robotics group. So why are we talking about robot intelligence? I think if you pay attention to the news or any I don't know if you read TechCrunch or these things, right? What the narrative is that's coming out right now is that embodied intelligence, embodied AI, spatial intelligence, right? There's a lot of words for it. Everyone is saying that this is the next big thing. And we're roboticists. We've been working on concepts related to embodied intelligence for some time. And I don't know about you, but I feel like, okay, people are finally starting to notice that robotics is the next big thing. So I'm really excited about this in general. I want to give a little bit of a timeline, right? I'm starting this year because actually startups that have things related to embodied intelligence, I have my citations down here, I'm thinking about companies like World Labs or Skilled AI, they've raised almost $1 billion just this year in total funding. This is not even counting our humanoid or our inspection or our more traditional kind of robotics startup. This is companies that are basically saying we're going to collect a lot of data and we're going to imbue intelligence in a particular way through the data that we collect. So this is even a subset of everything that you could say is embodied intelligence. It's exploding right now. It's not a brand new concept, right? We have, in 2006, some roboticists who published this book, How the Body Shapes the Way We Think. It's one that kind of discusses how different structures, different designs, right, could offload computation from something central into something kind of local or something that doesn't even require computation to begin with. The book is by Pfeiffer and Bongard, not Bongrad, there's a typo there, excuse that. And it's also got a foreword by Rodney Brooks. So this is more of a robotics kind of driven embodied intelligence emerging concept. Related to this, we have this concept called active perception, which was introduced by psychologists in the 1960s. The idea with this, and I'm showing a famous experiment with kittens. One of these kittens is empowered to move the carousel that it's rolling around. The other one is passive. What the psychologists showed in this actually somewhat cruel experiment is that basically the kitten that was not the world mover, which was not the one that was able to control the carousel, didn't develop its vision in the same way as the kitten that was able to interact with the world. So these ideas of active perception and structure, they kind of come together in a lot of the work that we're doing, right? And they're raising a lot of money. They're very important in the rest of the world, the popular world right now. And I want to go back just a tiny bit further into the past, into ancient history. So what do I have here? I have actually two things. The left-hand side is a clay tablet showing the Epic of Gilgamesh, in which the goddess Arubu creates a human out of clay. And the human he actually starts off as kind of half human. He only fully becomes human after he starts integrating into society and observing their customs, like their meal times, their rituals, things like that. On the right-hand side, I have Prometheus, also creating a human out of clay. And so really, you could argue that people have been interested in making embodied intelligence for millennia. But why now? Why is this getting really popular now? I think because we've had advances in, I'll call it unembodied intelligence, right? We have lots of virtual AI things that are very good, that are very, popular to talk about again, and very, changing a lot of things. And we have all these kind of applications where we love to just have something help us. So we're not maybe getting philosophical about creating ourselves, but we are at least looking for helpers in our homes, in industry, and maybe in healthcare, right, in various places. And what seems to be the narrative right now, again, like more in the news than what roboticists all might think, but is that we're going to reach this by collecting a lot of data. We're going to collect all the data, and we're going to fit, some good structures to this, and we're going to learn from doing that. And that's how we're going to be able to finally, after 2,000 years or whatever, reach embodied intelligence. So that's embodied intelligence through perception, right? And I think everyone can agree that active perception would be an important part of creating something that acts intelligently, right? I would argue that the shape and the structure and the actual physical existence of the robot in its environment is equally important. So a robot's shape, structure, and physics are going to matter just as much as the data it can collect. And this is what I want to kind of make the case for to you today through some of the research that our group is doing. We can notice that engineers have not yet designed the right robots for many, many tasks. And the ones that I'm thinking of are a little bit more human interactive, a little bit more requiring of delicacy. We have assistance, we have healthcare, we have entertainment, and we have exploration. So we've made progress in all these areas, but it can be hard to say, here's a specific surgical procedure, let's make a robot for that. Here's a type of environment that I want to explore, but I don't know much about it, let's make a robot that can do that, and have some guarantees about not damaging it or things like that. So we don't have the suite of engineering tools yet that we need to design a robot. What we would do instead, right, is we would probably look to purchase a robot. So we'd hop on over, maybe we're in Canada, we'd hop on over to ClearPath, we'd say, should I use an arm or something with wheels or a legged robot, right? That's what you kind of say if you wanted to explore something. You wouldn't say, can I create a morphology from the ground up? That's the question that I'm more interested in. So our research group, what we mainly do is we develop and we evaluate design modeling and integration frameworks for robots that have morphologies that you haven't heard of yet and that you can't buy. So what will I talk about today that's related to each of these things? First, I'll talk about a project related to co-optimizing the design and control of soft robots. So looking at a joint design control space, which is kind of a crazy, non-convex kind of space. The second thing we'll talk about is using solid mechanics to design shape morphing soft robots through auxetic lattices. And for those of you who don't know what that word means, I will tell you. Finally, we're going to look at some unpublished as yet work on proprioception through contact with the environment and deformation. So let's start with the first topic here. This work was published in RSS in 2022, and then follow-on work was published in Autonomous Robots in 2023. We're going to be co-optimizing the design and control of a soft robot. What do I mean by that? So let's say I have kind of just a bag of parts here. Let's say I have a body. The body's rigid, it's a disc. Let's say I have some legs. These legs are kind of like balloons. They're made of silicone. When you pressurize them internally with air, they bend. Can I make an arbitrary combination of these move forward? If I just attach the legs any which way, maybe to each other, maybe to the body, could I make that move forward? Maybe. Someone mouse maybe. Sorry, I need to keep the mic a little further away. Sorry about that. In general, no, right? But maybe yes. What would you do to design and control this system? What kind of thing would you put together? Do you want to think about it for about 10 seconds, and then I'll wait for an answer? So, some brave soul.
Some like evenly spaced legs on the side that we can twist in a way that allows them to move forward?
Yeah, so you'd put legs on either side, they'd be evenly spaced, and then you'd maybe like move them out of phase, right? That's kind of how we walk. That's also how spiders walk, you know. Lots of things walk like that. I would agree. I would say most roboticists would build something that looks like this. And this is one of the first soft robots that you'll ever see. It was published in 2011. What was neat about this was the casting framework to create this monolithically, and the fact that you can get emergent behavior here, right? So we have our air coming in through these pneumatic lines and going into the legs in an out-of-phase fashion to create this inchworm gait. So symmetric leg placement along two axes, periodic actuation, inspired by nature. How does this look? Good? You like it? Could we do better? Could we do better in more complicated tasks generically? But not, for now, just looking at this crawling task because it's one we can get our head around. Could we do better? I think maybe we could. The way that we could do better is by learning both the design and the open loop controller in a simulation setting. But then, of course, we have to deploy that in the real world and figure out if it actually works. So does it work well? Does it work as well as the simulator says it's going to work? Right? Who knows until we do an experiment. So that's what we actually did in this project. We used this kind of modified soft actor critic reinforcement loop here, reinforcement learning loop. So here you're seeing soft actor critic training an open loop controller on our robot. What's new is that in parallel with this controller, we're actually sampling many designs from a design distribution. So our design distribution is simply taking different robots that have a middle and different leg placements and different possible motions that those legs can do. And then it's updating that distribution over time. So our design distribution is this kind. If you're in physics, you'd call this a Boltzmann distribution. I think in computer science, they maybe call it something else. I'm not sure. But this is the math of what the distribution is. And what we basically have is where we start out with things uniform, and then we recurrently select those better performing designs over and over again as we iterate around this loop about 1 million times. So what we get, right, is we get a schedule for the entropy of this distribution. We have an entropy target that starts off, allowing a lot of entropy and goes down. And then we have this beta in our Boltzmann distribution that gets set based on what the entropy is supposed to be. So what we're kind of doing is we're selecting the best robots from the population over and over again. We're training a policy that works well for all of them, and we're rinsing and repeating. What do you need to accomplish this? Do you think I could build every robot and do that 1 million times on, let's see, this is a combinatorial space. It's got a middle. There's 8 slots for legs. Every leg can do one of 3 different motions. I think after you take out the symmetries, that's around 12,000 different robots. Can we design build our way out of this? No, right? And we can't buy one either, right? They don't sell this. So we're simulating, obviously, right? We're using a simulator called SOFA, Simulation Open Framework Architecture, which is a finite element simulator actually originally developed for surgical applications. But it has a really great soft robotics toolkit in it. So this can handle elastic materials, this can handle contact models, it can handle Coulomb friction, it's got damping, it's got dynamics, inertia, all the good stuff. The other thing that you can't really do when you have a flexible robot is just pop that into like Mujoko, right? It's not going to work as well. So we do this. It's slow. Raise your hand if you've used a finite element analysis software before. Is it slow? Yeah, so it's slow. So we can't live with that because we still have to analyze up to 12,000 robots 1 million times. So we end up taking a reduced order model of the robot. Now, okay, so we have 12,000 robots. We have reduced order models of all of them. Actually, reducing those models takes a lot of time, too. So we simplify that one step further. And since it's a modular construction of robot, we reduce it modularly. We reduce the legs and the body separately, and then we're able to cut and paste the different components together and get it to mostly behave well. We can do this within a tolerance. So the reduced model here, which considers kind of fewer nodes of your mesh in the FEA, has some tolerance, tau, in comparison with the full order model. So not only do we reduce it in this modular fashion, we get a guarantee of how accurate it's going to be. Maybe not how accurate to reality, right? That would be hard to measure, but at least how accurate it's going to be to kind of the industry standard of modeling of soft stuff, which is a good finite element model. So we do this, we run our loop, we learn, we get some answers. Not only do we get some answers, but we create a baseline here So a true expert who had recently finished her PhD in soft robotics used the literature to design this amazing baseline that has a symmetric gait and out-of-phase motion between the fore and the hind legs. The expert's design reaches a reward of 4.5 centimeters. That's how far it travels in about 20 seconds. The learned design does a little bit better, right? It reaches, in reality, it reaches around 10.3. In simulation, it reaches around 11.2. You can see kind of our histogram here of how the learning process went. What you have for this axis here is a little bit about what robots are most popular. So, right, 0 means that there's a lot of entropy in the distribution. No one robot is more likely than another. What we see is that as the forward progress goes up, we're selecting smaller populations of robots, and we're getting better performance as we keep training. You can see the emergence of a couple of different robot types. L1 is the robot that kind of won in our first run of this, and L1 through L5 performed comparatively the same or better compared to the baseline. So we can zoom in on that a little bit more. You can look at all of these robots, and you can look at how they performed in an experiment where we just kind of we made the robot, we ran it with the gait that the policy said it should have, and we measured how far it went. And you can look at their performance in simulation too. We're not quite within error of simulation, but we're doing fairly well, especially considering that this is a pretty tough thing to analyze directly. So what's going wrong here? You know, why am I at 4.3 versus 7.5? Why here am I a little bit negative versus 4.5? It's actually the friction model. So friction's affecting our sim-to-real performance a lot. One of our more performant robots, this L1 robot, is doing really well. So you have in light gray the line of where the center of mass of the robot would be in simulation. And then for this particular video, we hand tracked where the center of the robot was in the video. And so we have the real motion of that here. You can see as it does this sliding gait, it kind of leans back in order to slide forward, and it's tracking fairly well, all things considered. Especially when you consider that our simulated internal pressures are like very square and perfect, or the policy ones are, and the real ones have some slopes associated with them due to leakage and the fact that air takes time to flow out of the tube, right? So that looks nice. The one that looks less nice is the baseline. What we can say, at least, is that there's like some qualitative similarity between these waveforms. And then the last thing we can say is that the simulation actually is making slow forward progress, right? You can kind of see a slight slope upwards net there. But we catch it at a bad time, right? We end the simulation right here as it's leaning back to go forward. So if we ran this maybe for just a few more cycles, we would have seen forward progress there. And we would have seen that the main place where the model is incorrect is in this phase of the gait. So it's where the robot starts with its forelegs bent, and then it tucks up its hind legs beneath it. The simulation is saying that it should move backwards as it does that. In reality, it's moving forwards, and that's actually responsible for a big part of the gait. So as that kind of repeats, right, we'll get more and more cumulative error, but other parts of the gait will be pretty accurate, right? Not much change of the center of mass here, not much change in the simulation either. So what can we conclude about all of this? I think I want to show you a little bit of a video that's going to show some bloopers and going to show maybe how these crawlers actually differ from one another in reality. So here's one of our more performant robots. We tested this with a few different model order reduction tolerances. Our question being, as the model gets less and less accurate in this, one measure of accuracy, how much worse does the robot actually get? And we actually got good robots from all of the runs that we were able to try. We'd have to make the model a lot worse, I think, to see the sim-to-real go down much. And we got some weird gaits, all of which were asymmetric. So this one we jokingly called the Ferrari robot because it's the robot that went the fastest out of all our trials, and it is red. I don't think it would compete with a real Ferrari, but that's okay. And this is a gait that I could not have imagined, but if you look at it, it starts to kind of make sense. And the asymmetries start to make sense too. What's crucial about this one is you can see it right there. As it goes forward, it actually pivots on this foreleg. And that's sort of like what we do, right, when we're walking. We pivot, our legs act like pendulums. There are even pendulum models of walking. And that pivot, it lets it just go that much further compared to if it was in flat contact with the floor. If we keep accelerating through this video, which my slides don't let me do, so I'll just keep speaking here. If we keep accelerating through this, we're going to see some bloopers. And the bloopers that we're going to see are almost all going to be related to bad changes in sliding to sticking contact. So the stick to slip transition is going to be off compared to what the simulator said it would be. And then the robot is going to do something wrong. So hopefully we can get to the first blooper kind of soon. But for now, what I'll tell you is that there are a lot of asymmetric gates that we kind of discovered through doing this. I think, again, because they can introduce these asymmetric pivoting behaviors that, kind of allow it to go a little bit further. If you think about it, maybe that, if you squint, that resembles what we do when we walk. Let's see, is that one going to fall down? No. All right, is there a question I can answer while we wait here? Again, I will reset the video if I accelerate through it. Yeah?
But with these asymmetries, is this introducing lateral motion that might be undesirable in some other case?
Yeah, it is, but I would argue we didn't penalize lateral motion in our reward function.
Yeah.
And if anything, you orient that robot like 20 degrees off where you started it, then it's going to go even faster in the direction you want it to go. Yeah.
Did you use any different friction floors?
Yeah, so in the experiment we did, we used cardboard, very sophisticated, right? We used cardboard, table, and silicone mat. I tried to do this thing where I froze like a cookie sheet full of ice, but it kept melting on the electronics, so I got rid of that. Here's our blooper. He falls down. So we tried it, but I think I'd want to do more with this and maybe do it a little bit more rigorously. But what we did is we kind of fit these coefficients of friction with a spring scale, dragging a block across them. We popped those numbers that we had into the Coulomb friction of our simulator, and we trained on randomized frictions that were within that range that we had found. And we didn't find it helped like that much. It's really just about how many successful stick slips the robot can undergo. So I think what we'd have to do is we'd have to get it a little more rigorous, and what I really want to do next is I want to introduce a more complicated friction model, but make it fast also.
Did you try different kind of shoes on the tip?
Informally, yes. Like we had a fun afternoon of like putting different kinds of tape on it. But in the end, we felt that it should be the same material, just for like better comparison. So yeah. Anyway, here's one that fails. Kind of goes back and forth and then falls down. Yeah.
So in the scenario where for your baseline you had high deviation between real and sim, it seemed like the main error was in the very beginning, and then the shapes of the trajectories basically correlated quite highly.
Yes.
So is that something like this, tiny bias in the beginning like this, would you be able to fix it by getting real data and training a residual to the simulator?
I think that would be a great approach, especially if we don't have a friction model that we think is better or solvable or these things. Because computing around those discontinuities is really tough, and I think that that's actually the root of why it's happening. So yeah, I think a residual could be a nice solution. There's actually new work about that, training residuals on physics simulators for soft robots, which I'm reading slowly. Yeah, so anyway, here's some of our bloopers. Doesn't always work. Main source of error or of malperformance here is failed stick slip and weird moments that creates. So before anybody asks, you can see a tether here, right? Some pneumatic tethers. People always want to know, are those pulling on the robot? The robot weighs around 100 grams. Those weigh around 20 grams. And we have them kind of on a gantry thing so that they can follow the robot. So we're hoping not. Yeah. Anyway, here's another result that this is where we just tried to train the design that we thought was best without having that design population sampling in the loop. So you take a single design, you train it. Our policy's not working so well here. And the authors are kind of still arguing amongst each other about what that means. And is this a good ablation of, if you take out the design and you train only the controller, that it's bad, or is it just kind of a coincidence that none of these work? So that's a question that we're kind of thinking about. So, what can we conclude from co-optimizing the design and control of soft robots? Well, we can conclude that desirable open-loop behavior definitely can emerge from design choices. There are some designs we saw that were consistently better than other designs, even for the same kind of quality of control policy on them. And we can observe that, right? We can observe that these asymmetric designs got favored and they had distinct advantages. And then we can ask the question, what was more important for sim to real? Is it model quality? Is it, if we add noise to the model, could that make sim to real better? Was it the capability of this thing to search across the space that, made it find the ones with the most robust transitions in some way? That's a question we're still trying to answer. Okay. So I'll discuss the second topic now. Sorry, I don't know why it's making that noise. Sorry about that. Which is shape morphing soft robots using auxetic lattices. This was published in IROS 2023 and in RoboSoft 2023. Different pieces of research on the same topic. So an auxetic material is a material that has a negative Poisson's ratio. If you have a mechanical engineering background, you know what a Poisson's ratio is. If you don't, a Poisson's ratio is simply like, if I take this piece of material, I stretch it up and down, how much is it going to squeeze when I stretch it? And you can imagine if you take a rubber band, you stretch it, it's going to get smaller in the middle, right? Every material does this, except an auxetic material. An auxetic material has the opposite relationship. You can see that this beam structure is auxetic. If I stretch it in one direction, it'll expand in the perpendicular direction. Okay, and we can pattern these. I'm about to show you ways of patterning these. Then I'm going to explain why we can. So we can pattern these by kind of considering a beam-like element that looks like this. This is a polynomial. It's a Bezier curve with 4 control points. We can pattern our Bezier curves antagonistically in this way. You actually just saw an animation of one that moves in that way. And we can look at what happens to one of these when you pull on them and what forces actually accumulate due to the strain inside this beam. So the more curvature the beam has, I have D by L here, that's how much you pull it. I have my tensile force here, that's how much force the beam pulls back on you with. The higher this ratio, H by W, is, the flatter of a curve and then you get before transitioning to this kind of more steep trajectory. So we can make these lattices that have preset geometry. What are we going to do with it? I haven't told you yet. Maybe you can guess that it's shape morphing. We can make lattices that have preset geometry and have preset force-motion relationships. That's kind of fun, right? We can make that by patterning things. The things that we know how to pattern these beams on right now are a cylinder, which is where you lay out a rectangular lattice and then you wrap it around, assuring that certain compatibilities match, and a conic frustum, which is where you take your cylinder that you've patterned and then you kind of warp it so that you have this angular relationship. Again, you could cut that out on the page and you could roll it up and attach it. You can attach the cylinders to the cones and you can get shapes that undulate or that have different cross sections. So far, so good? Okay. So we made little devices that look kind of like this. They have thin cylinders attached by conic frusta to bigger cylinders, all of which are patterned with different types of beam lattices. They might be highly compliant beam lattices. They might be ones that don't move very much at all. Then we put a pneumatic bladder inside, and we attach that pneumatic bladder to an air hose. So we ran the air through the robot going this way. What do we think is going to happen?
Will expand?
Yeah, expand.
Yeah, it'll expand. Which of these modules will expand first? Will they all expand at the same time?
Does it depend on how fast you push the air inside? But
It does depend on that, yeah.
because otherwise, maybe at the same time if you're slow enough.
Yeah?
No?
Yeah, so if it's slow, maybe at the same time. If these cylinders are large in diameter, maybe at the same time. But if you have a jet of air at a certain volumetric flow rate, and you have larger and more compliant modules in yellow, coupled with less compliant constrictions in green, you get sequence out. And we took some videos for IROS that kind of explore this. So this is one of the examples that we made. I have our video of it as we inflate it going from top to bottom here. And you can see kind of, the air does continue to flow through the whole thing. But what you can see is that the first module reaches its max capacity first, followed by the second, followed by the third. Not only that, but the max capacity of every module is a little bit smaller as you advance along it. So there's some kind of a gradient that's happening here. So for instance, you could look at part A of the video. Part A of the video is this frame here at 4 seconds. The first module is very, very close to being full. The second ones haven't started to move much yet. And the way that we very sophisticatedly measured these volumes was using a script where a student would draw a square around the module, and then we did some geometry and some camera angle stuff to back it out. But we're working on a better experiment for that too. So you can see point A here, right? The first module is almost full. The other ones haven't really started yet. Then you can get to point B, where the first and second modules are full. The third one is getting there. And you can get to some rupture over here. So what happened there is that our pneumatic bladder actually broke. It got overpressurized. And then the volume got very large because the whole thing kind of shifted. So we can see that this, by hooking things together in this way, we get sequential motion. And we have a few toy examples of robots that you can make by using this idea. Now, why would you want to do this? So here we have 3 fingers. The fingers all move the same, but they have different attachment points to a common air source that's just off the page. Common air source happens to be a bike pump. That experiment happens to have been done during the pandemic by one of the undergraduate students that we were working with in her garage. But what you saw was that as you inflated the bike pump, one finger actuated the most and first, the second one actuated a medium amount and second, and the third one actuated a little bit and last. And we'll see more examples of this, either where the modules are in series or they're in parallel with different levels of compliance in the inlet of the air. So yeah, so what can you do with this? What you can solve is a problem plaguing pneumatic robots called the piping problem. So last section of this talk, I showed you a crawling thing. It had a big tether, right? It had a lot of tubes associated with it, right? What if it didn't need those? That'd be nice. In general, you find that pneumatic equipment adds a lot of bulk to these systems, which are supposed to be lightweight and nice. But you can't really achieve that unless you have cleverer ways of hooking them together. So we did some experiments with different levels of maximum volume, different levels of compliance at the pinch points, and we got different answers. I'm going to go ahead and get to the last part of the talk here. Actually, I might want to pause it for questions, because for the unpublished part of the talk, I think I want to pause the live stream, if that's okay. So yeah, do people have questions about what I presented so far?
Can you use another medium like oil or water instead of air?
For this? Yeah, so for the first one, I think it would be a little bit tougher because you're actually relying on pressurization. So you need a compressible fluid in there. This one, I think, other than being messy, it would actually be an easier experiment to do with oil because then you would have a set volume. You could even be measuring volume flow rates, and you actually wouldn't have to deal with that pressurization, and that would be very nice. Yeah.
In the first part of the talk, why learn one policy for all different morphologies instead of learning like a different policy for each morphology?
Yeah, so what we really wanted with that work was to have kind of all of it happen in parallel. And what we didn't want was you could imagine if you do this, right, you kind of would have to enumerate through all your designs and train the best policy on each one, which, it sounds good, right? But then how do you make that comparison and how long is that going to take training-wise? So what we were thinking was, if it's a good performing design, the policy, right, it was a neural policy, so it was kind of a complex representation of, something that mapped down to something very simple. We felt like it should be able to capture that, and we'll only have one loop that we have to do. There's no kind of inner loop. There's just one big parallel loop. The other thing that I'll say is the bloopers that you saw at the end of the very last video, that was where we took a single robot and we trained our policy with the same soft actor critic loop. For some reason that we, again, still don't fully understand yet, that didn't do as well. If I was personifying a machine learning algorithm, I would say that the policy likes to see a variety of robots and that helps it learn. But I'm going to stop short of saying that. So, okay, great. I'll let this video finish up. Here's an example of our domino effect robot actuator again. You can see a single air source coming in here with all those different levels of compliance at the pinch point. causing different motion, even though the center parts are identical, and causing order to the motion, even though the air is getting pumped into all of them at the same rate. All right, so last section of the talk is going to be about proprioception through contact and